Hello everyone, my name is Léonard Hussenot. I'm a research scientist in the Gemma team working on post-training. And this is how I like to think about the roles of pre-training and post-training in developing the best model possible. Pre-training, it's all about compressing the whole world's information. It trains on a whole bunch of data with this imitation learning loss, right? You just try to do exactly like in the data. You try to predict the next token given the previous tokens. And the output of pre-training is a simple yet extremely powerful next token predictor. On the other hand, post-training is about picking a personality for your model. It's about choosing a behavior among all the possibilities that you've seen during pre-training. What is the personality you want your model to have? It trains on much more targeted data and with very different losses than purely imitation loss. Robert mentioned a couple of them, first SFT, but then reinforcement learning, right? And post-training is the thing that turns a next token predictor into a product, right? It turns a model into a chatbot. And that's why I think as developers or as researchers, this is also a key stage in developing your applications. So what's interesting with post-training research is that it requires small model because you need to iterate a lot, right? These kind of algorithms are not as stable as purely imitation, as cross-entropy. So you generally need a family of model to scale from small model to very capable ones. But you need very capable models because you cannot do post-training on random models, right? You need already a very powerful pre-trained model to be able to conduct good research on post-training, right? So Gemma is absolutely marvelous for this because you get all these three sizes that allow you to conduct your research on the smaller one and then, grow as you go to bigger models. And that makes it a perfect family of model for post-training research. And actually, the recipe that Robert presented early that developed Gemma 2 and the version fine-tuned for Japanese, these algorithms for post-training, they were actually invented directly on Gemma, right? And that's what's really interesting. And I'm going to tell you about two examples of research directions that were developed thanks to Gemma, but also for Gemma. The first one is a reinforcement learning algorithm we like to call BOND for best of n distillation. Let me get into the details. So most of you might know best of n. It's a sampling method, right? It's instead, when I get a query, right, a prompt, instead of sampling only one answer from my model, I'm going to sample n, let's say 20. And I'm going to score these 20 with a reward model. And I'm only going to forward, I'm going to return the one that has the highest score. Very simple, very powerful. But most of you are developers. You know that you don't want to pay 20 times the price for each query you get, right? So that's not actually sustainable. So if it's yet strong and simple, you want to improve this. And this is the solutions we found. Actually, we realized that you can have an explicit formula for the behavior of the best of n sampling method, right? So you can express explicitly the best of n distribution based on your original distribution. And then it becomes a very simple distribution matching problem. You're going to learn a behavior that matches the behavior of your original model when it was sampling with best of n. So that when you sample only once from your model, you get the same answer that if you had run 20 samples from your first one, scored them, and return only the best one. And now you can serve your best of n distilled model and get the same performance with only one sample as if you had 20 samples, right? And that's really good. You will ask me, but you're adding more hyperparameters to my problem. And actually, no, n, it's quite easy. You don't choose it. Like it's not 20 during the algorithm itself. It can be solved by realizing that, best of n of best of n is just best of n squared, right? So if you just apply this algorithm iteratively, right, by taking your behavior, your policy, as we call it in reinforcement learning, and doing best of n of this policy, and then best of n of best of n of this policy, and distilling it in the previous version, you will get a stronger and stronger model. So here are a couple results, and they are actually on Gemma 1.1, because that's the results that convinced us to use this method on Gemma 2. So on Gemma 1.1, you see that compared to the PPO variant we were using before, we're actually improving both Gemma 2b and 7b, that was the sizes of 1.1, on both safety and instruction following dramatically, right? These are side-by-side scores as given by humans. So really nice method, and I encourage you to check it out because it's extremely simple, and it's already on archive. We can check the paper. You will now ask me, yeah, there's a problem. You talked about the reward model, right? You still need to be able to score, like in best of n for best of all distillation or any reinforcement learning algorithm. You need to be able to give a score to a prompt and a generation pair. And that's why I want to talk to you briefly about weight average reward models. So reward models, as Robert mentioned earlier, they are here to predict the human preferences, basically, right? You have a prompt, you have a generation, and the reward model will tell you how much a human would like this answer for this prompt. And what I'm telling you here is very simple. It's a trick to improve all your reward models. Whenever you train one, is just train several and average them in the weight space. That might sound surprising. It works extremely well. It works better than ensembling. It works better than most other techniques. And it's very simple because at inference time, when you use the reward models in reinforcement learning, you won't have to do anything. You now have a single model that is averaged, and you can use it as is. Right? And I'll go directly to the results, right? In yellow, you have the performance of reinforcement learning when you optimize an individual reward model. On the y-axis, this is a control reward. You can think of it as a ground truth reward. On the x-axis, you have the distance in the Kullback-Leibler divergence to the original model. So as you can see, during reinforcement learning, the model is going to be strained away from the original model, improve according to the ground truth, and then go down. And as you can see for the yellow curves, it goes down very quickly. But as you start averaging more and more models, for example, you added some diversity with data ordering or just data sets between all the runs between your reward models, and you average them. So you can average 2, and it improves this performance, right? At a given distance to the original model, you have a much higher performance in terms of ground truth reward. And as you average 6 and then 10, you're getting stronger and stronger performance. So, and anyway, you're going to tell me this is expensive, but we all know that you have to look for hyperparameters, that you always do several runs. So don't throw them away, just average them, and that works really well. Yeah, that's about it for these two research directions. And I just wanted to say again, Gemma is an amazing family of models for doing research. So I encourage you to check out Gemma for doing your research. But as developers, I also encourage you to look at this kind of research to turn great models into great products. Thank you very much.